Hey, so this is the integral we're going to solve today. Yes, it's an integral. It's a pretty beefy one. It's the integral from minus infinity to positive infinity of sine to the power 4x divided by x power 4 dx. And to solve this, we will need some trig and identity, which I have conveniently written out right here. And we're going to prove these two. These two are the one that doesn't seem to make most sense, but I will take the time to prove out. So first thing first, let's take from the original definition here, which is sine A plus B is going to equal to sine A cosine B plus sine B cosine A. This is a super classic result. There's a bit of the description by black pen, red pen that will actually prove everything visual. However, what we are curious is sine A cosine B. Well, let's take sine A plus B, and we plus sine A minus B. Well, what would that be? That would actually be something that is very nice. So I'm gonna copy this because I'm too lazy to type. Actually twice here, and let's just using this because it would make it a bit easier. Because it's minus, we get a minus sign here, and what this will give us is sine A plus B plus sine A minus B equals, these two terms conveniently cancel out. This plus this is just 2 sine A cosine B, and if we divide both sides by 2, we will get 1/2 here equals sine A cosine B, which is the result we have above here. Next up, let's go and get prove the second result, sine cube of A. Well, this result right here is not too hard to prove per se, but we're gonna derive that by using the fact that sine cube A equals sine A times the sine squares of A. And here you can use the power production properties to reduce this to 1 minus the cosine of 2A. The proof of this I will just leave as an exercise for you. You to exercise some trigonometry. Very fun in my opinion. But basically you just take the cosine 2A's here and you can simply expand that out. Expand this into like cosine A plus A, and you can just simply simplify it. It's not just a very simple trivial proof here. I will not really go into details. So here let's take the 1/2 outside, this 1/2 here, and we will get sine A minus sine A times cosine 2A. And here is a super nice result. We just proved what the sine of A plus sine A cosine B is. Well, in this term, B is actually just 2A. So we can take this at 1/2 times the product, the sine of the sum of the inside here, which would be 3A, plus the sum of the minus, which is A minus 2A, which would be minus A. And remember that since sine is a odd function, we can pull the minus outside, give us this instead. This is the closing bracket in the outside. And what this gives us is very simple. Sine A minus, the minus with the minus cancel to become the plus. So we can get 1/2, which will give us this. So it will be 1/2 times sine A minus 1/2 sine 3A plus 1/2 sine A. So here we go. Sine A plus 1/2 sine A is just 3/2. 3/2 times 1/2 outside gives us 3/4. Actually we don't even have to. We can just simply, we can keep it here for now. 1/2 times, this will be 3/2 sine A minus 1/2 sine 3A. And now to get rid of the 1/2, 3/2 here, let's factor 1/2 outside. Will give us 1/4, because 1/2 times 1/2 is 1/4, and this will be 3 sine A minus sine 3A. And that is a really nice result, because what this allows us to do is turn any cube of sine into just a simple like factor of this one, and you can simply resolve it later. So now let's get back to our original, let's get back to our original derivative here. Sorry, our original integral. This integral right here, we're going to use a very famous, very well-known trick, the Feynman's technique. Let's first define the parameter I sub a, use a lot of a in this one, to be honest, as the integral from 0 to from minus infinity to positive infinity of the sine to the power 4 of ax divided by x to the power 4 dx. Notice that if I set a equal 1, we get back the original integral. That's how we're going to solve it. We're going to try to solve this parameter, and simply once you get that in the form of like some form of like f of a, then we can just simply substitute a equal 1 and we get back this original integral here. So now let's differentiate both sides with respect to a. We will get d over dA of I sub a. You can also just simply turn it into a simple integral. I decided not to. I want to just differentiate one first because there's actually this is a formula for it. It's a little bit complicated, which is why I decided to go for this trick instead to turn this, because there's a formula for the third one that seems simple. So there's multiple ways to solve this integral. This is just how I first solve it, or how I originally solve it. So let's bring the derivative inside. Let's do d over dA of the integral from minus infinity to positive infinity of sine to the power 4 of ax divided by x to the power 4 dx. This will give us I prime sub a equals, let's bring the integral inside, let's bring the function inside, will give us, bring this inside here, then will give us the integral from minus infinity to positive infinity of the partial derivative of a times the sine to the power 4 ax over x to the power 4 dx. Now I know that there's more to solve this one. There's like for contour, projection. Oh, that is very fun. But I like Feynman's. I really like Feynman's technique. I think it's really fun to use. It's also very easy to understand too. So this is what I'm up with. This is what I come up with. This is what I first solved this integral. Anyway, it's a really fun one, to be honest. It's a groups of family. So this is what I find to be the most spectacular, to be honest. And yeah, let's go ahead and let's try and solve this. So here we'll get the integral from minus infinity to positive infinity. Since x to the 4 is a constant with respect to a, we will get x to the power 4. The derivative here will be 4 sine cube of ax times the cosine of ax thanks to the chain rule, multiplied by x dx. As you can see here, this x and this x now cancel, so we can get this power up to 3 instead. How nice is that? And here we can use the formula minus infinity to positive infinity, which is proof of the sine cube of something. Here we go. So let's go and solve this to 1 over x cubed times 4 times 1/4 of 3 sine x minus sine 3x 3ax. I'm sorry, this should be 3ax. I don't know why, I forgot. 3ax times cosine of ax times dx. And as you can see, these 4 and this 4 simply cancel out. So now we get the integral from minus infinity to positive infinity of 1 over x cubed times, let's bring that to the numerator because it makes more sense. And let's also multiply this out. So we get 3 times 3 times sine ax cosine ax. I don't know why my writing is being terrible. Minus sine 3ax times cosine of ax. Terribly sorry about all that writing. And now let's invoke another fantastic trick identity, which is the sine of something times the cosine of something is equal to 1/2 of the sine of 2 of that thing. So what this is 3/2 times the sine of 2ax. And the reason why I'm going to be serious soon, because we're going to also use the product rule we just proved earlier, which will be equal to 1/2 times the sine 3ax plus ax is going to be 4ax However, 3x, and we can actually break the bracket out here. Just to break the bracket out for easier, minus 1/2. It's basically just this row here, but you factor out the bracket. So I'm going to solve custom step here. 1/2, 3x minus 2ax is going to be 2ax. And as you can see, the 2ax and the 2ax here very nicely cancel each other out, giving us a really awesome result, which is that the first derivative of I sub alpha is going to be equal to 3/2 times 1/2 going to be 2 times sine of 2x, 2ax, sorry, minus 1/2 times the sine of 4ax. And now we have solved this into, we have turned this integral into something that's actually solvable. Now if you look at this and say, how is this solvable? Well, terribly sorry about that. Let's get back to it. So over here, we get into this something that is actually solvable. And you look at it and say, how is this solvable? It is look insane. Well, we're going to use Feynman's technique a couple more times to turn this into something that we actually know, which is the Dirichlet integral. And you're going to understand what it is. If you don't know what the Dirichlet integral is, well, you can skip. Timestamp chapter should be in the description below. But if you don't, I will actually go and prove the Dirichlet integral y here as well. So this is the first derivative of I sub a. Now let's differentiate both sides with respect to a, and this time we're going to do a bit of a cut hand here, because if I write all this out, it's going to take like 2 hours. So here, the derivative of sine 2ax with respect to a, well, the 2 is a constant, let's multiply 2 out. The derivative of sine something is going to be cosine of 2ax. And obviously, thanks to the chain rule, we need to multiply with the derivative of the inside, which would be 2x, because we're doing with respect to a, minus 1/2 times the 4 times the cosine of 4ax, multiplied by 4x dx. Sorry, x cubed dx. And here, as you can see, the x and x cancel with this x here, give us a square term. And you might realize something. Every single time we differentiate this, we actually reduce the term by 1. That's the key. So now, once again, let's differentiate both sides with respect to a one more time to give us the third derivative of a here, equal the integral from minus infinity, that is a tail infinity sign, to positive infinity, that also a tail infinity sign. 2 times 2 is 4 here, which is just a constant, multiplied by the, so it will be minus 4 times the sine of 2ax, multiplied by the derivative inside here, thanks to the chain rule, obviously, 2x, minus 4 times 1/2 is going to be 2, multiplied by the 4, multiplied by the derivative of the cosine, which is going to be minus sine. So we're going to solve that to become plus sine. The minus and minus cancel here. Basically, 4 times 1/2 is 2, the derivative cosine, it's just minus sine. The minus cancel with this minus. Multiplied by 4x, obviously, because the derivative of the inside, chain rule. Multiplied by x squared, got the dx here. And once again, this x, and this x here gladly cancel. Which means, finally, we will get the third derivative of of a is equal to the integral of minus infinity to positive infinity of minus a sine of 2x. And here I'm actually going to do something pretty funny. I'm going to separate this variable out. So we're going to separate this into 2 small integral. First thing first, let's separate this into minus a times the integral from minus infinity to positive infinity of sine of 2ax multiplied by divided by x dx, plus this is also going to be 8, right? I think it should be 8. Wait a second, I think there's something wrong here. Let's see, I think 2 4 2. Wait a second, let me give me a couple seconds. I think I need to double check this result. Okay, I'm back, and I just realized a mistake here. 3/2 minus 1/2 is actually equal to 1. which means we don't have this 2 here, which means that this is just going to be a 2 over here, and this is going to be equal to a minus 4. Oh, terribly sorry about that one. Yeah, 3 half minus 1 half equal 1, not 2. I thought it would be 3 half minus 1 half equal 2 over 2, and it will be 5 minus 1 half. It just, basically this also work. I just need to multiply the outside by 1 half. That will also work. I just forgot. That is my bad, and I sincerely apologize. So, this is minus 4 to this is minus 4 times the integral from minus infinity to positive infinity of sine 2ax over x dx plus a times the integral from minus infinity to positive infinity of sine over 4ax divided by x. I don't know why I'm writing it infinitely worse into 2 seconds dx. Now, those who already know how the Dirichlet integral works can easily call this answer out to be, this would be 2 pi. However, if you don't know what the Dirichlet integral is, I won't go here and, actually not 2 pi, this would be 4 pi, I'm sorry. So let's go ahead and actually solve this integral right here. And if you want to skip to the part where we just do the rest of the integral, feel free to skip to the timestamp. I don't know how long it will take. Into below, should probably have some chapter, but otherwise, let's go ahead and actually solve. So this one here, if we do a simple u substitution here, let's substitute 2ax equal u, which means that we will get dx here will equal u over 2a, du over 2a, and x equal u over 2a. Similarly, if we substituting v, we substitute 4ax equals v, then we get dx equals v over dv over 4a, and x equals v over 4a. So what this integral going to become is the integral from the triple derivative, the total derivative of a equals minus 4 times the derivative of the integral from minus infinity to positive infinity of sine of u over 2a times du over 2a. And as you can see, these 2a here very much cancel out, so I'm going to clear them off. These 2a cancel out. Look how nice. I forgot to actually delete this part too. Plus a times the integral from minus infinity to positive infinity of sine of v divided by v over 4a times dv over 4a. And same result before, these 4a cancel, which will give us sine v over v dv. And if you know the Dirichlet integral, which I told before, this is actually going to be equal to pi. I will go ahead and actually show a proof of how this is actually equal to pi. If you don't want to see it, again, feel free to skip, but otherwise, let's dive straight into the sub-problem in this integral here. Let's calculate the I sub 2 here as equal to the minus infinity to positive infinity of sine over x dx. Here, notice that this is actually an even function, so we can just turn this into 2 times the integral from 0 to positive infinity of sine over x dx. So this will be very useful. This only works because it is an even function. Remember that the original formula is not an even function, so we actually can't do that, I think. But anyway, it doesn't really matter that much, but we're going to turn this into an even function here. Now, let's use Feynman's technique one again. However, instead of this time, set the parameter as sine of ax time over x. Let's set this parameter to something actually solvable. And this setting parameter will need some try and error. This time, we will set the parameter e to the minus 2ax times the sine of x over x dx. And here we will need to go ahead. The reason why we can set it is because if we want to do the differentiation trick, we need to make sure that this thing absolutely converge, and this converge obviously because that's actually infinity, this thing approaches 0, so it converge, and that's actually really useful when we know. Now let's differentiate both sides with respect to a. We will get the integral from 0 to positive infinity of minus x times e to the ax. Remember, this is with respect to a, not x, by the way. times sine of x over x dx. See that these two x cancel out, so we're quickly going to remove them. We're also going to move the minus sign to the outside, and we get this lovely integral. And now to solve this integral is very simple. Let's do integration by parts. So the way we're going to do integration by part is we're going to multiply both sides here of this one, multiply this integral with minus a over minus a. And what this allows to do is, well, first thing it's going to be minus times 1 over minus a. Let's put the minus a outside because it's a constant, times the integral from 0 to positive infinity of minus a times e to the minus ax times dx times sine x. And the reason why you see me arrange like this is this term right here is actually just the d of e of minus ax. If you differentiating this, you get this one back. So what this allows to do is these minus term cancel, which will give us 1 over a times the integral from 0 to positive infinity of sine of x times d of e to the power of minus ax. And here we can use integration by part now. Let's go do a quick IPP here. It will give us 1 over a times sine of x times e to the minus sine of e to the minus ax, evaluate from 0 to positive infinity minus minus the integral from 0 to positive infinity of e to the minus ax times the derivative of this one. Oh, okay. Oh, some update. Okay, the one I'm using is I have a bit of a coping. I think we just use a lot. Yeah, I don't really blame it. So times the cosine of x dx. So we take u dv equal uv minus v du. If you don't know what it is, I'll quickly roll it, which is in the part. So the derivative of sine x is going to be cosine x dx. And now, once again, let's take this, let's evaluate this thing right here. Well, first thing first, let's evaluate the this value here. As x approaches infinity, this thing approaches zeros. So the first term is going to be 0. As x is 0 here, so this is going to be e to the power of 0, which is 1. Sine of 0 is 0, which means we get 0. So this term just completely vanishes. So that doesn't really change at all. So let's do that. Now that this term has officially vanished, we will get the minus here, and once again we'll multiply both sides. We'll multiply this with minus a over minus a to bring this derivative inside here. So since we multiply with minus a, we will get the positive of minus a, which will be 1 over a multiplied by the integral from 0 to positive infinity of cosine x times d over d of e to the minus ax. It's the exact same stuff that we see above here, as you can see. And the reason why is we can do a not the integration by part. This is 1 over a squared times cosine of x times e to the minus ax, evaluate from 0 to positive infinity, minus the integral from 0 to positive infinity of e to the minus ax times sine x times dx. And the reason why it's important is because this actually we minus, so we're going to cancel this and put it to the plus. Basically, derivative of cosine x is sine x dx. So multiply that, the minus sine x dx. So the minus cancel with this minus here. And we get this super gorgeous result where this thing here, well, plus infinity is to get to 0, so that's 0. Plug in 0 here will give us 1. Cosine of 0 is just 1. Cosine of 0 is 1, and this is 1, so it's be 0 minus 1. And this term right here is the exact same as this term right here. Well, it differs by a minus. As you can see here, that and this looks exactly the same. So we can substitute that as follow. We can substitute that by now the derivative of I2 primes of a equal 1 over a squared times 0 minus 1 minus I prime sub 2 sub a. And now this becomes an integral, a very solvable solution. It's a very simple equation here, and an equation we can actually solve. So let's solve it. Let's multiply both sides with a square. So we get this equals, that is a bit of a table writing there, equals 1 equals, well, this will be minus 1 minus I square of a. Now let's add both sides to a square. Let's add I prime of this, no, this is not square, what am I doing? I 2 primes of a to both sides. So plus, oh my god, what is that writing? Plus, let me zoom a bit more. I prime 2 of a equals minus 1. And what this means is now we're going to factor out I primes of 2a. So when we get us 1 plus a square equals minus 1. And now let's divide both sides with 1 plus a square, which is always non-negative, which is always positive actually. Minus 1 divided by 1 plus a square. And now that we get this result, what we can do to recover back our original function, because remember, we want to find this function here. Because if we find this, what this parameter is, we just plug in a equals 0 and we get back I sub 2. So let's go. To do that, we're going to integrate both sides with respect to a. We'll get I prime 2a dA equals integral of minus 1 over 1 plus a square dA. And here, this is going to be I2 of a. And this is a very famous one. If here you're going to do u sub u equal tangents of a. And you're going to work this out to be the inverse, to be the minus, because the minus are here. But the integral actually equals the inverse tangents of a plus a constant c that we don't know. However, we can determine this constant c. And how can we determine this constant c? Well, let's bring back our original I sub 2 here. This is, oh, that's not the one. This is the I sub 2 we are trying to find, as you can see here. So now let's let the limit as a approaching positive infinity of I sub 2. Well, what would happen here? Well, as a approaches infinity, this thing here approaches 0. This whole integral now collapses to just 0. And as a approaches infinity to our top one, well, inverse tangent to infinity is just going to be pi over 2. So we get this to be pi over 2 plus c. And now we will get c to be c1, by the way. The rules of c1 you will see soon, because we will actually do the exact same trick to recover back our original one. Now you see what we're differentiating a lot. We're just going to do a triple integration to get back our result. Super, super nice. So here, c1 is going to equal to, well, pi over 2. What that means is we get our original parameter I2 of a is equal to the minus inverse tangents of a. I don't know why my writing is just terrible there. Of a plus pi over 2. Now, we want to find back the original solution to the integral here, which we were finding is actually the integral from 0 to positive infinity of sine x over x. Well, it's not exactly the case, but it's actually, we only want to find this one right here. The integral from minus infinity to positive infinity of sine x over x. But remember, since it's an even function, we can just split into half and we get this integral right here. Well, now we have I2. If we plug in I2 here equals, if we plug in equals 0, well, this is going to be inverse tangents of 0, which is 0, which means this integral right here equals pi over 2, which means that the original integral, this integral right here, from the integral from minus infinity to positive infinity of sine x over x dx equals pi. How nice is that? Well, and that's the dilution integral, and that will be the very quick shortcut we need to take detour to solve this integral above here. So if you come in from the timestamp, you skip ahead, welcome back. We just finished solving the Dirichlet integral. Very common type you might see here. Now let's get back to solving the original integral. Here it is. We are finding the triple derivative, the third derivative a is equal to minus 4 times the integral from minus infinity to positive infinity of sine u over u du plus a times the integral from minus infinity to positive infinity of sine over v dv. So here, using the knowledge we just put above, which is this integral equal pi, we can just simply sub it in, minus 4 times pi plus a times pi, which will actually equal to 4 pi. And now we can start recovering back our original integral. So let's integrate both sides with respect to a again. This will be, that's 4 dash. The third derivative of I primes of a dA, well, very simple, it's going to be 4 pi dA, and this will be equals to I, the second derivative of a, equals 4 pi times a dA, 4 times a plus a constant c. And the way to determine this constant c, we just simply bring the integral, we bring the second derivative here, which is this chunky boy over here. And now if we bring this boy down, you see it looks intimidating. However, if we substituting a value like 0, well, look at this. This is going to be 2 times the cosine of 0, which is 2. This is going to be 2 times the cosine of 0, which is also 2, which means we get 2 minus 2 equals 0. So this whole integral just collapsed into a beautiful 0, which means that C2 equals 0, since a equals 0 here too, you know. We fix this pi, but that pi looks terrible. So we get the second derivative of a equals 4 pi times a. Now let's integrate again to recover back. So the second derivative, integrate both sides here. The integral from the integral of the second derivative of a dA equals the integral of 4 pi a dA, and this one is just going to be the I primes of a equals this one will be 4 pi times a square over 2 thanks to the power rule. The 4 and the 2 will cancel, so we're just going to get, ultimately we're going to get back a 2 and the plus a constant C3. Now once again, we're going to find a constant C3 here by simply pulling our I primes of 2 here, which is not that one, unfortunately. It is this bad boy right here. Again, these looks really intimidating, and they do look a bit intimidating. I did not copy. Ouchie, I did twice. There we go. Here, and let me delete some of them. So it looks intimidating. However, if you let I primes of 0, well, voila, sine 0 is 0, sine 0 is 0, the whole integral also collapses to 0, which means beautifully C3 is also just 0, which means that now we get the I primes of a here equal to 2 pi a square. Okay, cool. Now let's integrate both sides one last time. Yes, one last integration, and finally we can bring back, recover back our original parameter. And so here, what we're going to get is, well, it's going to be I of a, obviously, we get I of a. But this is going to be 2 pi times a cubed over 3 plus a constant, the C4. And what is I sub a? Well, remember that what we define I sub a. Well, I sub a is just the integral from minus infinity to positive infinity of sine to the power of 4. Sorry about that. Sine to the power of 4 a x divided by x to the power of 4 dx. And well, if we substitute in a equals 0 to this to this integral where we get 0, which means that the fourth constant is also 0, which means that we get I sub a equals 2 pi over 3 times a cubed. I think, right? It's a cubed. Yeah, yeah, so the first derivative, basically it's 3 here, so the first one gives us a, the second one gives us a square, and the third one gives us a cube. Okay, that's correct. And now we can finally solve our original integral. The original integral at the form is the integral from minus infinity to positive infinity of the fourth powers of sine x divided by, that 4 looks a bit too big, so make it a bit smaller. There we go. Over x to the power 4 dx. Well, since we know I sub a equals 2 pi over 3 times a cubed, and I sub a is just this, substituting a equal 1 gives us back our original integral, and at a equal 1, I sub a is actually just simple, 2 pi over 3, and that, ladies and gentlemen, is the original solution to the problem. The integral from minus infinity to positive infinity of the fourth power of sine of x divided by x to the power 4 dx is 2 pi over 3. How amazing is that? It's very, looks simple integral, but very intimidating. Requires lots of refinement and even a quick detour for the dilution integral between. If you already know, we can skip a lot of this. But yeah, lots of trig, integration by part, use substitution, lots of trigonometry, all to go back to a very, very nice and super cool solution. And that is all I have today. I will see you again. If I ever make any more math videos, it'll be a miracle. But yeah, see ya.